The ground beneath your feet is a lie. Gravity, the force that seems most real and fundamental, might be a cosmic mirage. This startling idea comes from the cutting edge of theoretical physics, suggesting gravity is not a fundamental force at all. It could be an emergent phenomenon, a collective illusion born from the quantum entanglement of spacetime itself. By the end of this journey, you will see the universe in an entirely new light. We will explore how the very fabric of reality is being rewoven, confronting what happens to information inside a black hole and why the flow of time itself might be an illusion. What does it mean for our most basic experience of reality if the force that holds us down is just a shadow of a deeper quantum world? An apple falls from a tree in a quiet English garden, and the world changes. Isaac Newton saw in that simple fall a universal truth, a force that governed not just the fruit but the moon itself. He formulated his law of universal gravitation, a single mathematical idea that could explain the arc of a thrown ball and the majestic orbit of planets. This was the powerful idea of action at a distance, a mysterious tug between any two objects with mass, an invisible force acting instantly across the emptiness of space. It was a monumental success. For the first time, humanity could predict the tides and the paths of celestial bodies with stunning accuracy. Gravity was enshrined as a fundamental force, the undeniable architect of the cosmos. Yet, this beautiful framework contained a deep conceptual itch. How could the sun reach across 93 million miles of void to pull on the Earth? What was the mechanism? Newton himself was deeply troubled by this, famously writing that the notion of gravity acting without any mediating substance was so absurd that he believed no thinking person could ever accept it. He had given the universe a rule book, but the reason behind the rules remained a profound and unsettling mystery, a quiet crack in a classical pillar that pointed toward a revolution waiting to happen. That conceptual itch Newton felt would fester for over 2 centuries until a young patent clerk in Switzerland dared to scratch it. Albert Einstein completely reimagined the cosmic stage. He proposed that space and time were not separate, rigid absolutes, but were fused into a single, dynamic entity called spacetime. Think of this spacetime not as an empty container, but as a vast, invisible, and flexible fabric. This fabric is the true protagonist of Einstein's theory of general relativity. A massive object like our Sun does not reach out and pull on the planets. Instead, it sinks into the spacetime fabric, creating a deep well of curvature. The Earth is not being pulled, it is simply following the curve of this warped geometry, like a marble rolling around the rim of a giant cosmic bowl. This path of least resistance through curved space is called a geodesic. What we feel as the force of gravity is just this natural motion along the invisible contours of the universe. The genius of this geometric picture was its incredible power. It predicted that light itself would bend as it traveled through warped spacetime, a phenomenon confirmed during a solar eclipse that made Einstein a global icon. It foretold the existence of gravitational waves, ripples in the fabric of spacetime, which we now detect from colliding black holes billions of light years away. And it gave us our modern picture of black holes, where spacetime curvature becomes so extreme that not even light can escape. Yet for all its success, general relativity presents us with a beautiful and profound puzzle. If spacetime is a malleable fabric, what precisely is it made of? What are the threads of this cosmic cloth? The theory describes the fabric's behavior with perfect elegance, but it says nothing about its underlying composition. It is like having a perfect mathematical description of the surface of the ocean, detailing every wave and ripple while having no concept of the water molecules that constitute it. This geometric perfection, this final theory of gravity, points irresistibly toward a deeper, more fundamental quantum origin. But while Einstein was mapping the grand geometry of the cosmos, a revolution was brewing in the opposite direction, deep within the atom. Down in the quantum realm, the very idea of a predictable, smooth fabric of spacetime shatters into a storm of probability. Here, particles are not tiny billiard balls. They are ghostly smears of possibility, existing in multiple places at once, a state known as superposition. An electron is not here or there, it is a wave of potential, a set of probabilities described by the Schrödinger equation, only settling into a definite location when we force it to by making a measurement. This is a world ruled by chance and inherent uncertainty, where the act of observation itself shapes reality. The solidity of matter dissolves into a dance of quantum fields, a kind of invisible, energetic medium that fills all of space. What we call a particle is just a localized excitation in its field, a tiny knot of vibrating energy. This leads to the strangest quantum property of all, entanglement. Two particles can become linked, their fates intertwined. Measure the spin of one entangled particle, and its partner, even if it is now on the other side of the galaxy, instantly assumes a corresponding spin. They communicate faster than light, not by sending a signal through space, but by acting as a single, non-local entity. This bizarre, chaotic, and profoundly probabilistic foundation is the bedrock of our most accurate theories of matter. Yet it stands in stark, violent opposition to the serene, deterministic curvature of Einstein's gravity. One theory paints a picture of a smooth, warped canvas. The other reveals a canvas that is itself a seething, probabilistic foam. The central conflict of modern physics is this: our two most powerful descriptions of reality are written in completely different languages, and they refuse to speak to one another. So this is the great confrontation, a battle of titans for the soul of reality itself. On one side stands general relativity, a theory of breathtaking beauty that describes the cosmos on its grandest scales, from the dance of galaxies to the bending of starlight. On the other stands quantum mechanics, our wildly successful rulebook for the atomic and subatomic worlds. The problem is that these two rulebooks are written in languages that are completely and utterly incompatible. This is not a minor disagreement. It is a fundamental schism in our understanding of the universe, and it rears its head in the most extreme environments imaginable. Picture the very center of a black hole, or the very first instant of the Big Bang. In these places, enormous amounts of mass and energy are compressed into an unimaginably tiny volume. According to general relativity, spacetime here should curve into an infinitely dense point called a singularity. But infinity is not a physical answer. It is a sign that your mathematics has broken down. This is where quantum mechanics insists on having its say. It tells us that at such incredibly small scales, the very idea of a smooth, continuous spacetime fabric is a fiction. Instead, spacetime itself must become a chaotic, seething, and probabilistic foam. Tiny wormholes might blink in and out of existence. The geometry of reality would be fluctuating wildly, with no definite shape or distance. This is the quantum foam, a concept so turbulent it makes the idea of a simple, warped fabric impossible. When physicists try to force general relativity's equations to work in this quantum realm, their calculations often explode into nonsense, producing infinite results that have no physical meaning. These infinities are a screaming alarm bell, a clear signal that our understanding is fundamentally flawed. This clash is far more than a mathematical inconvenience for theorists to tidy up. It is a profound philosophical crisis. It suggests that one of these pillars, or perhaps both, is not the final word. They are approximations, incredibly accurate in their own domains, but merely shadows of a deeper, more complete theory that we have not yet discovered. The search for this ultimate theory, a theory of quantum gravity, is the single greatest quest in modern physics, and it is on this very path, while trying to reconcile these two giants, that a radical idea began to take shape. What if gravity is not a fundamental force to be quantized at all? What if it simply emerges from the quantum chaos, an illusion born from a more basic layer of reality? The path toward a solution began with the darkest objects in the universe. When physicists like Jacob Bekenstein and Stephen Hawking studied black holes, they made a shocking discovery about information. Hawking showed that black holes are not truly black. They slowly evaporate by radiating particles, eventually vanishing entirely. This created a terrifying paradox. Quantum mechanics states that information is never destroyed. If you burn a book, in principle, every single letter could be recovered from the smoke and ash. But if a black hole evaporates, what happens to all the information about the stars and planets it swallowed? It seemed to be erased from existence, violating a sacred quantum law. Bekenstein, however, had a brilliant insight. He realized a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume. Instead, it is proportional to the surface area of its event horizon. This was a profound clue. It suggested that everything happening within the three-dimensional volume of a black hole, every particle, every bit of data, could be perfectly described by information stored on its two-dimensional boundary. This is the seed of the holographic principle. Think of an ordinary credit card hologram. The flat, shiny surface contains all the data needed to project a stunningly detailed three-dimensional image that seems to float in space. The holographic principle proposes that our entire universe operates in a similar but far more fundamental way. The three-dimensional reality we experience, with its stars, planets, and ourselves, might be a magnificent projection. All the information that makes up our world could be encoded on a vast, distant, two-dimensional surface. This is not a metaphor for a simulation. It is a serious proposal about the nature of spacetime itself. If this is true, then gravity, the force that shapes the cosmos within this volume, cannot be fundamental. It must emerge just like the three-dimensional image from the flat surface. It is a side effect, a consequence of the way information is processed and projected from the underlying quantum code written on the boundary of reality. This radical blueprint provides the first concrete framework for how a seamless, continuous force could arise from a more fundamental, pixelated quantum world. This thermodynamic view of reality offers a breathtakingly simple answer to the mystery of gravity. It suggests that gravity is not a fundamental force at all, but an entropic force. This is a concept we encounter in everyday life. Think of a simple rubber band. When you stretch it, you feel a pull, a force resisting the stretch. This isn't a fundamental force of nature. It is an entropic force. The polymer chains in the rubber are tangled and disordered, a state of high entropy. Stretching them forces them into a more ordered, aligned configuration, which is a state of lower entropy. The entire system wants to return to its maximum entropy state of comfortable disorder, and that tendency is what you feel as an elastic pull. Gravity, in this radical new picture, operates on a cosmic scale in precisely the same way. The physicist Ted Jacobson made this connection stunningly precise. He demonstrated that you can derive the entire, complex mathematical framework of Einstein's general relativity, the very equations that describe black holes and the expanding cosmos from one simple starting point, the fundamental laws of thermodynamics. How is this possible? The key is to think of spacetime not as a smooth, pre-existing stage, but as a system built from an unimaginable number of microscopic, quantum components. We do not yet know what these components are, but we can describe their collective behavior using thermodynamics, the science of heat, energy, and probability. Jacobson showed that if you assume every small patch of spacetime obeys the most basic thermodynamic principles, Einstein's equations for gravity emerge automatically. In this view, what we perceive as the force of gravity is the universe's overwhelming tendency to maximize its entropy, to move toward a state of greater hidden information. When a planet orbits a star, it is not being pulled by a force. It is following a path that allows the microscopic constituents of spacetime to explore the greatest number of possible arrangements. The curvature of spacetime itself is a direct manifestation of an entropy gradient. A massive object creates a region where the entropy, or the amount of hidden information, is higher. Everything else simply moves to maximize the total entropy, flowing downhill on a slope of information, just as heat flows from a hot object to a cold one. This reframes our entire cosmic story. Gravity is no longer the primary actor. It is a collective illusion, a statistical mirage born from the relentless, probabilistic drive of countless underlying quantum bits to disorder themselves. It is the universe's most powerful and pervasive example of emergent behavior, a simple rule arising from unimaginable complexity. So if gravity emerges from a cosmic drive toward disorder, what is the substance that actually gets disordered? The answer appears to lie in the strangest of all quantum phenomena, entanglement. This ghostly connection, where particles share a single existence across vast distances, is far more than a curious laboratory fact. It is now believed to be the fundamental glue that weaves the very fabric of spacetime into existence. Think of the basic building blocks of reality as individual, separate quantum threads. On their own, they are just disconnected points of information, a formless and chaotic dust. But when these threads become entangled, a remarkable thing happens. A correlation is established between them. They are no longer independent. It is this network of correlations, this web of quantum relationships, that begins to define a geometry. Physicist Mark van Romsdonk provided a stunningly elegant thought experiment to illustrate this. Imagine two completely separate, non-entangled quantum systems. In this state, they are like two distinct universes with no connection whatsoever. There is no spacetime bridge between them. Now, introduce just a single thread of entanglement between the two systems. Instantly, a tiny, wormhole-like bridge forms, a geometric connection in the emergent spacetime. As you increase the amount of entanglement, weaving more and more threads between the quantum components, this bridge strengthens and solidifies. The empty void between them transforms into a smooth, continuous fabric. The entanglement literally stitches together the geometry of space itself. This insight turns our intuition inside out. We are used to thinking that two particles become entangled because they are close together in space, but this new view suggests the reverse is true. They are close together in space because they are entangled. The proximity, the very distance between things, is a manifestation of the strength of their quantum connections. This leads to a dramatic and profound consequence. If you were to somehow cut these threads of entanglement, the fabric of spacetime would not just warp, it would fundamentally unravel. The smooth geometry would dissolve back into a disconnected, non-spatial dust. This is not merely theoretical. Calculations show that if you gradually reduce the entanglement between two regions, the emergent space between them stretches and pinches, eventually tearing apart completely in a geometric rift. This suggests that the force we feel as gravity is not a primary actor pulling on things. It is the spatial manifestation of the underlying quantum system trying to maximize its entanglement. A planet orbiting a star is simply following the path of highest entanglement entropy, moving through a geometry that is itself defined by a vast cosmic loom of quantum connections. The curvature of spacetime is a story written in the language of entangled information. The smooth, continuous spacetime of Einstein's universe is a magnificent illusion. If we had a microscope powerful enough to peer down to the very foundations of reality, to a scale a billion times smaller than an atomic nucleus, we would not find a seamless fabric. We would find a storm at this level known as the Planck scale. The serene geometry of general relativity dissolves into a seething, discrete network. Space is not smooth, it is pixelated. These pixels are not laid out like a static grid, however. They form a dynamic, ever-changing web of connections, a structure physicists call a spin network. Each line in this network carries a fundamental unit of area, and each intersection or node carries a tiny volume. This is the atomic structure of space itself. There are no empty containers here, no stuff inside space. The network is space. Its connections define its geometry, and its evolution defines the flow of time. The dynamics of this network are not random. They are governed by precise mathematical rules, a framework known as loop quantum gravity. In this picture, the nodes and links of the spin network vibrate, interact, and reconfigure themselves in a cosmic dance. What we perceive as a perfectly smooth, three-dimensional space at our human scale is like the calm surface of the ocean. From a distance, it appears continuous and fluid, but we know it is ultimately composed of a vast number of discrete water molecules. In exactly the same way, the smooth, warping spacetime of planets and stars emerges from the collective, averaged behavior of trillions upon trillions of these vibrating quantum grains. This is where gravity finds its true origin. Think of a gas trapped in a box. A single molecule whizzing around has properties like mass and velocity, but it does not have pressure. Pressure is not a property of any one molecule. It is a collective, statistical property that only emerges when you have a vast number of molecules colliding with the walls. You cannot understand pressure by studying a single atom in isolation. You must study the system as a whole. Gravity, in this radical new view, is precisely the same kind of phenomenon. It is not a fundamental force mediated by a particle. It is a thermodynamic effect, a hydrodynamic property of the underlying spin network. The curvature of spacetime that guides planets is not a primary quality. It is the large-scale average of the dynamics of the network's microscopic constituents. Much like the pressure of a gas is the average force of its countless molecular collisions. What we feel as the relentless pull of gravity is simply the universe's quantum geometry settling into its most probable, highest entropy state. This shifts our entire perspective. We are no longer living on a curved stage, but within a cosmic computation, a dynamic process where space and time are generated by the relationships between fundamental bits of quantum information. The force that seems most real to us is a shadow, a collective echo from a world of breathtaking simplicity and chaos. This radical thermodynamic view of gravity finds its most audacious champion in the work of Erik Verlinde. He presents a direct and controversial challenge to our most basic assumptions, proposing that gravity is not just emergent, but an entropic force driven by information. His argument begins with a simple, almost startling premise. that space is fundamentally a storage device for information. Think of the entire universe as a vast cosmic hard drive, with every tiny Planck-scale pixel capable of holding a single bit of data. Now introduce a material body like a star or a planet into this sea of information. Verlinde's key insight is that the presence of this mass disrupts the information landscape. It effectively hides some of the information in the universe, reducing the total entropy that is accessible to an outside observer. The system, in its relentless drive toward maximum disorder, responds to this. It exerts a force to move the mass in a way that restores the entropy, that makes the hidden information accessible again. This restorative tendency is what we have called gravity for centuries. It is not a fundamental attraction, but a statistical push, a consequence of the universe trying to maximize its information content. The rubber band analogy becomes even more powerful here. When you stretch the polymer chains, you are forcing them into a more ordered, lower entropy state. The pull you feel is their collective desire to return to a messy, high entropy tangle. In Verlinde's universe, a planet sitting in empty space is like a stretched polymer. The very presence of the planet imposes a kind of order on the informational vacuum around it. Gravity is the cosmic pullback toward maximum information disorder. The most staggering part of this formulation is its mathematical rigor. Verlinde demonstrated that starting only from these basic principles of information and entropy, one can derive Isaac Newton's entire law of universal gravitation. The familiar equation, with its masses and inverse square law, simply pops out as a natural consequence of the statistical behavior of information bits. This is a profound unification, connecting the world of gravity directly to the world of information theory without needing any fundamental gravitational force. But Verlinde's theory goes even further, making a testable and revolutionary prediction. When applied to the vast scales of galaxies, his equations for emergent gravity suggest a modification to Newton's famous law. For centuries, astronomers have observed that stars at the outer edges of galaxies orbit far too quickly. According to Newtonian gravity, these stars should be flung off into deep space. The prevailing explanation for this has been dark matter, a hypothetical, invisible substance whose gravity provides the extra pull. Verlinde's framework offers a dramatic alternative. He calculates that on these enormous scales, the entropic force of emergent gravity naturally produces an extra gravitational effect, one that perfectly mimics the presence of dark matter. In his view, dark matter is not a missing particle, it is a ghostly mirror, an illusion created by the way information is stored and processed on a cosmic scale. This is not just a philosophical idea. It is a concrete, mathematical framework that challenges the very foundations of physics and offers a potential solution to one of astronomy's greatest mysteries, all by accepting that the force that binds the cosmos is nothing more than a memory of information wanting to be free. Of course, the idea that gravity is an emergent illusion is not accepted by all. This radical paradigm faces fierce and legitimate skepticism from much of the physics community. The central criticism is that, for all its conceptual elegance, emergent gravity remains more of a compelling philosophical framework than a complete predictive theory. While it beautifully derives the basic equations of general relativity from thermodynamic principles, it struggles when the cosmic rubber meets the road. In the most extreme environments, like the violent spirals of two merging neutron stars or the chaotic maelstrom of the early universe, the full mathematical complexity of Einstein's theory presents challenges that the emergent picture has not yet fully overcome. Critics point out that a true theory must not only recover the old successes, but also make new, precise, and testable predictions in every scenario, a bar that emergent gravity has not yet cleared. This is especially true for its most famous prediction regarding dark matter. While Erik Verlinde's calculations show that emergent gravity can mimic the effects of dark matter in galaxy rotation, many astronomers point to other lines of evidence that are harder to explain away. They highlight the bullet cluster, a system of two colliding galaxies where the visible matter and the gravitational lensing effect, which acts as a map of mass, have been violently separated. The lensing shows a huge amount of mass where there is very little visible matter, a result that seems to perfectly fit the model of a cloud of dark matter particles that barely interact, sailing right through the cosmic collision. For many, this is a direct, observational proof that dark matter is a substance, not an illusion. Prominent physicists like string theorist Juan Maldacena, while acknowledging the power of the thermodynamic approach, caution that it may be a piece of a larger puzzle rather than a replacement for our current understanding. He and others argue that the evidence for gravity as a fundamental force, described by a quantum particle called the graviton, is still overwhelming within the standard model of particle physics. The debate is far from settled. It is a live, contentious, and wonderfully messy process, a testament to a field in vigorous, healthy flux. The very existence of this conflict shows that we are on the frontier, where our most cherished ideas about reality are being stress-tested, and where the next great discovery could come from either side, or from a synthesis no one has yet imagined. The profound beauty of these ideas is matched only by the immense challenge of proving them. How do you test a theory that suggests the very stage upon which our experiments are built is an illusion? The most dramatic effects of quantum gravity are not happening here on Earth, or even within our solar system. They become significant only at the unimaginably tiny Planck scale, a realm of energy and density so extreme that probing it directly is far, far beyond our current capabilities. It is like trying to see the individual pixels on a movie screen from the very back row of a vast theater. Yet, physicists are ingenious, and they have devised a suite of indirect searches, clever ways to look for the faintest shadows cast by this deeper reality. One promising avenue is to look for the ancient echoes of creation itself. The cosmic microwave background, the faint afterglow of the Big Bang, is the oldest light in the universe. It carries an imprint of the universe's infancy, a time when quantum fluctuations in the primordial foam were stretched to cosmic proportions. By mapping this relic radiation with exquisite precision, observatories like the Planck satellite are searching for subtle statistical patterns, tiny deviations from the predictions of standard cosmology that could be the fossilized signature of a pixelated spacetime. Another frontier lies in the most violent events in the cosmos, the collisions of black holes. When these monstrous objects spiral together and merge, they shake the very fabric of spacetime, sending out ripples known as gravitational waves. Our detectors like LIGO and Virgo have opened a new window onto the universe by listening to these waves. Now, scientists are meticulously analyzing the signals, hunting for any subtle anomalies in the ringing of the final black hole. Does the waveform match perfectly with Einstein's predictions, or are there tiny deviations, faint whispers suggesting that spacetime is not perfectly smooth, but has a discrete, grainy texture? To amplify this search, we are building a new generation of observatories. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will place 3 spacecraft in a giant triangular formation, millions of kilometers apart, to form a gravitational wave observatory in the quiet of space. Free from the seismic noise of Earth, LISA will be sensitive to lower frequency waves, allowing us to listen to the mergers of supermassive black holes and potentially hear the quantum hum of spacetime itself. But perhaps the most creative tests are happening not in deep space, but in laboratories here on Earth. Physicists are building analog systems to mimic the behavior of black holes and curved spacetime. One of the most remarkable involves Bose-Einstein condensates, a state of matter where atoms are cooled to near absolute zero and begin to behave as a single quantum wave. In this exotic fluid, scientists can create sonic analogs of event horizons, points where the flow of the fluid exceeds the speed of sound, trapping sound waves just as a black hole traps light. By studying how these analog horizons radiate and interact, we can test the thermodynamic principles thought to underpin emergent gravity in a controlled tabletop experiment. The quest to experimentally validate these radical ideas is pushing our technology to its absolute limits. It is a painstaking, incremental process, a search for the faintest of clues in the data. Yet it represents the next great frontier in physics, a direct assault on the deepest mystery of all, the nature of reality itself. This cosmic shift in perspective forces us to confront the ultimate paradox, the black hole. If gravity is an emergent phenomenon, then the very definition of a black hole must change. We must revisit the terrifying information paradox, but now with a new set of tools. The old picture was simple and grim. An astronaut falling toward a black hole's event horizon would, according to Einstein's pure general relativity, feel nothing special at the point of no return. They would cross this invisible boundary and be smoothly stretched and compressed toward the central singularity, their information seemingly lost forever as the black hole later evaporates into random Hawking radiation. This is the paradox, the destruction of information which quantum mechanics forbids. The conflict became even more acute with the proposal of the firewall. To save quantum mechanics, some theorists argued that the event horizon could not be a smooth, empty space. Instead, it must be a blazing wall of high-energy particles, an incinerator that burns up the astronaut long before they cross, thus preserving the information by never letting it enter. But this solution creates its own problem, violently contradicting the smooth spacetime of general relativity. We are left with a terrible trilemma, where one of three cherished principles must be wrong. Either information is lost, Einstein's equivalence principle is violated by a firewall, or quantum mechanics is flawed. The emergent gravity viewpoint offers a breathtaking escape from this trap. If spacetime is a tapestry woven from quantum entanglement, then the event horizon is not a special physical surface or a destructive firewall. It is simply a boundary in the entanglement landscape. Think of it as the shoreline of an island. From far away, the ocean looks like a single, continuous body of water. But the shoreline marks a transition, a place where the connections between water molecules change their pattern as they meet the sand. The event horizon is similar. It is not a wall of fire, but a region where the pattern of entanglement between the quantum threads of spacetime undergoes a dramatic rearrangement. For an astronaut falling in, the horizon is not a brick wall. It is a phase transition like water freezing into ice. The quantum information that constituted the astronaut does not get destroyed at a firewall. Instead, it gets scrambled and transferred. It is meticulously encoded into the intricate, microscopic vibrations of the horizon itself, a process known as quantum hair. As the black hole evaporates via Hawking radiation, this radiation is not random. It is subtly imprinted with that very information, carrying it back out into the universe. The black hole is not an information-destroying monster. It is the universe's most complex and efficient quantum computer, a system that scrambles and eventually returns all the information it receives. This resolves the paradox without needing firewalls or accepting information loss. It preserves quantum unitarity, the sacred rule that information must be conserved, by redefining the black hole's interior not as a separate realm, but as a highly entangled part of the external universe. The event horizon is the interface where this profound encoding happens, turning a cosmic catastrophe into a computational process and restoring order to the quantum laws of reality. This staggering mismatch between prediction and observation is known as the cosmological constant problem, and it represents the single greatest failure of numerical prediction in the entire history of science. Our two most successful theories, quantum field theory and general relativity, collide here with catastrophic results. Quantum theory tells us that the vacuum of empty space is not truly empty. It is a seething, bubbling soup of virtual particles that constantly flicker in and out of existence. This quantum jitter assigns a tremendous amount of energy to every single cubic centimeter of the cosmos, an energy that, according to Einstein's equations, should produce a powerful gravitational repulsion. When you calculate this predicted energy density, the number you get is astronomically large. Now we can also observe the actual expansion of the universe. We measure the rate at which galaxies are flying apart from one another, an acceleration driven by a tiny, faint pressure we call dark energy. The observed value of this energy is incredibly small. The problem is the gap between these two numbers. The theoretical prediction for the vacuum's energy is one followed by 120 zeros times larger than the value we actually observe. To get the theories to match our reality, we would have to fine-tune the cosmological constant with a precision that is utterly absurd, like balancing a pencil on its tip for billions of years in a hurricane. This is not just a small error, it is a crisis that suggests a deep flaw in our understanding of how gravity couples to the quantum world. An emergent gravity framework, however, rewrites this entire problematic story from the ground up. The core of the issue lies in a fundamental assumption that all forms of energy, including the quantum vacuum energy, must gravitate. They must source the curvature of spacetime in exactly the way Einstein's equations prescribe. But what if this assumption is wrong? If gravity is not a fundamental force, then the rules change completely. In an emergent thermodynamic picture, gravity is not a direct interaction, it is a collective consequence. It arises from the statistical behavior of the microscopic degrees of freedom that constitute spacetime. In this view, the vacuum energy of quantum fields is just another form of energy. It is part of the underlying microscopic system, but crucially, it does not necessarily have to couple to gravity in the simple, direct way we have always assumed. Think of it like this: the air in a room is made of molecules whizzing around with tremendous kinetic energy. This energy contributes to the air's pressure and temperature, but it does not directly contribute to the gravitational pull of the room itself in a simple, one-to-one way. The gravity of the room emerges from the collective mass energy of all its contents, not from the frantic motion of each individual air molecule. In a similar way, the frantic energy of the quantum vacuum could be largely decoupled from the emergent gravitational field. It is part of the internal, microscopic energy of the system, not an external source that directly warps the geometry. This leads to a profound shift in the nature of the cosmological constant. In Einstein's original theory, it was a free parameter, a number that had to be put into the equations by hand. Its tiny, observed value is the source of the fine-tuning nightmare. But in the emergent gravity paradigm, the cosmological constant may not be a parameter at all. Instead, it could be an integration constant. In mathematics, an integration constant is not a number you choose, it is a number that is determined by the boundary conditions of the problem. For example, if you drop a ball from a specific height, the equations of motion tell you its speed, but the starting height itself is a boundary condition that nature provides. Erik Verlinde's framework suggests that the value of the cosmological constant is set in a similar way. It is not a freely adjustable dial, but a fixed outcome of the total amount of information in the universe and the way that information is encoded on the cosmic horizon. The vacuum energy is still there, seething and bubbling, but its gravitational effect is neutralized, screened, or renormalized by the very process of spacetime emergence. The incredibly small value we measure for dark energy would then be a natural consequence of the universe's global structure and its holographic nature, not a bizarrely fine-tuned accident. This would dissolve the 120 orders of magnitude problem, not by finding new particles or forces, but by changing the very question we are asking. We would stop asking why the vacuum energy is so small, and start asking why the universe has the specific holographic boundary conditions that yield the gentle acceleration we see. The problem transforms from a catastrophic failure of calculation into a deep question about the cosmic initial conditions, a mystery that feels far more manageable and profound. This leads us to a question that cuts to the core of our existence. If space is an emergent tapestry woven from quantum threads, then what about time? Our most direct, visceral experience of reality is the relentless one-way flow of time, the feeling that the future is constantly solidifying into the present and then receding into the past. Yet in our two most fundamental theories, time is treated as a mere background parameter, a static stage direction against which the drama of physics unfolds. In Einstein's Relativity, time is woven into the four-dimensional fabric of spacetime, but it remains a coordinate, a dimension that can, in theory, be traversed just like space under extreme conditions. In quantum mechanics, time is an external, classical clock that ticks outside the quantum system, used to measure the evolution of probabilities. Both theories take time for granted as a primitive, fundamental ingredient. But if we are dismantling the foundation of space, can we really leave time untouched? The answer from the frontier of quantum gravity is a resounding no. This is known as the problem of time, and it is one of the most profound conceptual hurdles in all of physics. When physicists attempt to merge general relativity with quantum mechanics, time often simply vanishes from the core equations. The most famous example is the Wheeler-DeWitt equation, a proposed cornerstone of quantum gravity. This equation describes the entire universe in a single, timeless wave function. It has no time variable in it at all. The universe it describes just is, a static, frozen block of all possible configurations. This seems to be a catastrophic failure, completely at odds with the dynamic, changing world we live in. How can a theory that has no time possibly describe a universe where change is the most undeniable fact of our experience? The emergent paradigm offers a stunningly elegant resolution. If space emerges from a network of quantum correlations, then time might emerge from the evolution of those correlations. Think of the spin network, the fundamental fabric of reality. Its nodes and links are not static. They are dynamic, constantly updating and reconfigured. The flow of time we perceive could be the macroscopic result of this microscopic computation, the gradual shift in the pattern of entanglement between the universe's fundamental bits. Our conscious experience of moving through time from one moment to the next could be a side effect of this cosmic processing. A powerful analogy is a movie. A film is not a flowing substance, it is a series of still frames, each one a complete, timeless image. When these frames are projected in rapid succession, our brain perceives a smooth, continuous flow of motion and time. In the same way, the fundamental quantum description of the universe might consist of a vast set of correlated, timeless snapshots. What we call the passage of time is the brain's interpretation of this rapid sequencing of different network configurations. This idea turns our intuition about cause and effect completely on its head. We think that time flows and causes things to happen, but in this view, the happening is what creates the illusion of time. The relentless drive of the quantum system to maximize its entanglement entropy, to explore new correlations, is what generates the sequential ordering we call past, present, and future. This suggests that at the most fundamental level, the universe is timeless. There is no flowing river of time. There is only a vast, complex, and interconnected quantum state. The arrow of time, the reason we remember the past but not the future, could then be linked to the increase of quantum entanglement, a cosmic progression toward greater and greater complexity of connections. Your sense of self, your stream of consciousness moving from one thought to the next, may be the most intimate and personal evidence of a deep cosmic process where the universe is computing itself into existence, moment by illusory moment. This grand puzzle of quantum gravity has generated two towering intellectual cathedrals, each attempting to complete the cosmic picture. The first, string theory, reimagines the fundamental ingredients of reality. It proposes that at the very smallest scales, the point-like particles of the Standard Model are not points at all. Instead, they are tiny, vibrating loops of energy, unimaginably smaller than an atom. Just as different vibrations on a violin string produce distinct musical notes, the different vibrational modes of these fundamental strings give rise to the entire particle zoo, from electrons to quarks. Crucially, one specific pattern of vibration within the theory has all the right properties to be the graviton, the hypothetical quantum particle that would mediate the gravitational force. In this framework, gravity is fundamentally quantum because it is carried by this vibrating string mode, but the story goes much deeper, leading directly to emergence. These strings do not move through a pre-existing spacetime. They live and interact on dynamical surfaces called branes, short for membranes. The geometry of spacetime, its curves and warps, is not a primary stage. It emerges from the collective interactions and dynamics of these strings and branes. Spacetime becomes a secondary, derived concept, a holographic projection from a world without built-in geometry. The force of gravity, mediated by the graviton string, emerges from this deeper, vibrational reality. The second great approach, loop quantum gravity, takes a more direct and radical path. It does not replace particles with new objects. Instead, it insists that we must quantize the stage itself, the fabric of spacetime. It proposes that space is not continuous, but is woven from a dense network of discrete, finite loops. This is the spin network we encountered earlier, a dynamic web where each line carries a tiny, fundamental unit of area. There are no gravitons in this picture because there is no fundamental force of gravity to quantize. Gravity is not a force. It is the thermodynamic manifestation of this evolving spin network. The smooth, curved geometry of general relativity emerges in the same way the smooth surface of water emerges from the chaotic motion of molecules. When you look at the cosmos from a distance, the frantic dance of the quantum loops averages out to produce the serene, warping spacetime that guides the planets. One theory introduces new fundamental objects whose dynamics produce emergent spacetime. The other quantizes space itself, from which gravity emerges as a thermodynamic effect. They start from opposite ends of the problem, with string theory originating from particle physics and loop quantum gravity growing from the quantization of geometry. Yet, remarkably, their paths are converging. Both frameworks, through vastly different mathematics, point toward the same profound conclusion: gravity, as a fundamental force, is an illusion. It is a derived phenomenon, a collective behavior that arises from a more basic, non-gravitational layer of reality. Whether that layer is a symphony of vibrating strings or a dynamic tapestry of quantum loops, the message is the same. The force that feels most real to us is a magnificent and powerful shadow. So at the very bottom, what is the universe made of? The 20th century physicist John Archibald Wheeler offered a startlingly simple answer with his famous phrase, "it from bit." He proposed that every particle, every force field, even the fabric of spacetime itself, ultimately derives its existence from binary answers to binary questions. Is it here or there? Is it spin up or down? At the foundation of everything is not matter, not energy, but information. This is the radical proposition of digital physics, a view of the cosmos as a vast, ongoing quantum computation. Reality is not just described by information, it is information. The world we perceive is the output of an unimaginably complex calculation running on the hardware of the universe. In this pancomputationalist view, what we call a particle is simply a stable, persistent pattern of information. A force is a rule for how information interacts. And spacetime is the emergent operating system, the stage that arises from the relentless processing and correlation of these fundamental bits. This perspective elevates information from a mere abstraction to the primary physical entity, the fundamental stuff of existence. The cosmic computation does not run within space and time. It actively constructs them through the relationships it forges between bits. This is where a profound mathematical discovery provides a crucial bridge. Physicists have found a deep and unexpected connection between the abstract world of information theory and the tangible geometry of spacetime. The link is quantum error correction. In our own digital world, error-correcting codes are what allow a scratched DVD to still play a perfect movie, or a satellite to send a clear signal through cosmic interference. They work by embedding information in a redundant, distributed way, so that even if part of the physical medium is damaged, the original message can be perfectly reconstructed from the intact pieces. It turns out that the holographic universe operates on precisely the same principle. The information that makes up our three-dimensional reality is not stored locally, point for point. It is scrambled and spread out across a two-dimensional surface, encoded in a massively redundant quantum error-correcting code. This encoding is not just a neat trick, it is what creates the geometry of spacetime itself. The distance between 2 points in space is not a fundamental property. It is a measure of how difficult it is to correlate the information at those two locations. If the quantum error-correcting code linking them is strong and highly entangled, the points are close together. If the code is weak, they are far apart. The smooth, continuous space we move through is an illusion of scale, the macroscopic result of a microscopic reality where every spatial relationship is defined by the robustness of quantum information links. Gravity, in this ultimate reduction, is a direct consequence of this informational dynamics. The force we feel is the universe's tendency to maintain the integrity of its cosmic code. A massive object creates a region where the local information density is extremely high, which distorts the error-correcting landscape. The geodesic paths that planets follow are simply the trajectories that best preserve the coherence of the information network. The curvature of spacetime is the physical manifestation of the universe protecting its data from corruption. We are living inside a cosmic quantum computer, and gravity is the emergent force that arises as it tirelessly processes information, maintaining the consistency of the reality it is rendering all around us. The weight of your own body, the solid ground beneath your feet, might be the universe's most convincing magic trick. This notion of emergent gravity does more than just rewrite physics textbooks. It strikes at the very heart of our philosophical understanding of reality. For centuries, the dominant worldview in science has been reductionism, the idea that to understand a complex system, you simply break it down into its smallest, simplest parts. Understand the atoms and you understand the molecule. Understand the molecules and you understand the cell. This bottom-up approach has been spectacularly successful, leading us from the periodic table to the double helix. But if gravity is emergent, then reductionism hits a fundamental wall. You could know everything there is to know about a single quantum thread in the spin network, every detail of its state and vibration, and yet you would find no trace of gravity, no hint of curvature, no whisper of the force that shapes galaxies. Gravity is not a property of the parts, it is a property of the whole, a collective behavior that only manifests when an astronomical number of these parts interact in a specific, organized way. It is a stark reminder that the whole can be greater than and fundamentally different from the sum of its parts. This supports a rival philosophical view known as emergence or holism. Think of a familiar example, the wetness of water. You can study a single, isolated water molecule with perfect precision. You can know its bond angles, its vibrational modes, its every quantum property. But you will never find wetness. Wetness is not in the molecule. It is a new property that emerges only when trillions upon trillions of these molecules interact, forming a liquid with cohesive and adhesive forces. Though wetness is real, it is not an illusion, but it exists at a different level of complexity. In exactly the same way, the force of gravity appears to be a genuinely new property that emerges at the colossal scale of the cosmic spin network. It is as real as wetness, but it is not fundamental. This shifts our entire perspective on the architecture of reality. The universe is not just a bag of tiny billiard balls following simple rules. It is a layered reality, with new laws and phenomena springing into existence at different scales, each layer requiring its own language and concepts to be understood. This has breathtaking implications that reach far beyond physics, touching the ancient mystery of consciousness itself. Your mind, your thoughts, your sense of self are intimately tied to the physical brain, a network of nearly 100 billion neurons. A single neuron is a fascinating biological machine, but it does not think, it does not feel, it does not possess consciousness. If you adopted a strictly reductionist view, you might assume that by cataloging every neuron and every synapse, you would eventually find the consciousness hidden within the circuitry. But what if consciousness, like gravity, is an emergent phenomenon? What if it is a new, non-physical property that arises from the unimaginably complex, dynamic network of the brain as a whole? Your conscious experience would not be located in any one neuron, just as gravity is not located in any one quantum of space. It would be a real, high-level pattern that emerges from the collective dance of its parts. This suggests that reality is not built from bottom to top, but exists in a rich hierarchy of levels, each with its own authentic reality. The feeling of the chair against your back, the sound of a loved one's voice, the force that keeps you rooted to the planet, all of these are genuine experiences at the human scale, even as they dissolve into something entirely different when we look closer. We are not living in a universe of simple, solid stuff, but in a cosmos of relationships and connections, a vast, interdependent web where what is fundamentally real depends profoundly on the level at which you are looking. This concept of emergence is not some fringe idea invented for gravity alone. Physics is filled with stunning examples where collective behavior creates entirely new realities. Consider the very air around you. It has a property we call temperature, a single number that tells you if it is hot or cold. But if you could shrink down to the atomic scale, you would find a chaotic storm of molecules whizzing in every direction. A single air molecule does not have a temperature. Temperature is a meaningless concept for one particle. It is a collective, statistical property that only emerges when you have a vast number of molecules. The familiar feeling of warmth on your skin is not a fundamental sensation. It is the macroscopic average of trillions of microscopic collisions. This is the core of thermodynamics, a powerful description of the large-scale world that emerges seamlessly from the statistical mechanics of countless tiny parts. The laws governing heat and energy are not written into each atom, they arise from the crowd. Another breathtaking example is superconductivity. Take an ordinary metal and cool it to incredibly low temperatures. Suddenly, all electrical resistance vanishes. Electrons, which normally bump and jostle through the material, losing energy as heat, now pair up and flow in a perfect, frictionless river of current. This is a new phase of matter, a superconducting state. You could study a single, isolated electron for a lifetime and never predict this bizarre behavior. Superconductivity is not a property of individual electrons. It is an emergent phenomenon born from the complex, coordinated dance of countless electrons interacting with the lattice of the metal itself. The whole system acquires a property that is absent in any of its parts. For a more everyday analogy, think of a traffic jam on a highway. No single car is designed to create a jam. Each driver is simply following the car in front, trying to maintain a safe distance. Yet, from this simple, local behavior, a large-scale, persistent structure emerges, the traffic jam, which seems to have a life of its own. It can move backwards against the flow of traffic, and it persists long after the initial cause, like a slow-moving truck, has left the highway. The jam is a real thing, but you cannot find it by inspecting any single car. It exists only in the relationships between them. These examples reveal a profound pattern in nature. Time and again, we find that complex systems exhibit collective behaviors, new laws and phenomena that are not just hidden in their components, but are genuinely novel. They represent a new level of reality. This established pattern makes the idea of emergent gravity far less radical. It places it squarely within a respected scientific tradition. We are not inventing a new kind of magic. We are applying a well-tested principle to the most fundamental stage of all, the fabric of spacetime. The force that binds the cosmos may simply be the next and grandest emergent phenomenon we have yet discovered. For centuries, the holy grail of physics has been a single, elegant equation, a theory of everything. This ultimate dream was to unify the four fundamental forces of nature, to show how gravity, electromagnetism, and the strong and weak nuclear forces are all different facets of one beautiful underlying symmetry. But if gravity is not a fundamental force, this entire quest must be radically reimagined. The goal is no longer to unify gravity with the other forces, because gravity is not in that elite club. It is not a force to be unified, but a phenomenon to be derived. This is a profound paradigm shift, moving from unification to derivation. The new and more fundamental quest is to find the mother theory, the non-gravitational quantum system from which everything else emerges. This underlying theory might not look like a theory of physics at all. It could be a quantum field theory that does not know about space or time, or perhaps a vast matrix model, a kind of abstract quantum computer operating on a lower dimensional boundary. From the complex interactions and entanglement within this boundary system, a magnificent illusion is projected. the three-dimensional universe with its stars and planets simply pops out. The other forces, electromagnetism and the nuclear forces, along with all the particles of matter, are also born from this holographic process. They are not unified with gravity, they are all siblings emerging together from the same primal quantum source. In this breathtaking new picture, the familiar forces of nature are not separate threads to be woven together. They are different shadows cast by the same underlying object, distinct manifestations of a single, coherent quantum system. The search for a theory of everything is not abandoned. It is transformed into a deeper, more humbling, and far more exciting journey to find the source code of reality itself. This clarification is absolutely essential. When we say gravity might be an illusion, we are not saying it is not real. The ground will still hurt if you fall on it, and planets will continue to trace their orbits with perfect fidelity. The illusion is not in the effect but in our interpretation of its origin. In physics, an emergent phenomenon is every bit as real as a fundamental one, its power and predictability undiminished. The difference lies in its explanation. An emergent property is not a ghost, it is a new layer of reality that arises from the collective, organized behavior of a system's more basic parts. It is a genuine feature of the whole that you simply cannot find by scrutinizing any individual piece. Think about the solidity of the table in front of you. To your senses, it is a hard, impenetrable barrier, a fundamental fact of your world. But we know this is an emergent reality. That table is actually over 99% empty space, a vast void populated by a frenetic cloud of quarks and electrons. The solidity you feel is not a property of any single atom. It is the powerful electromagnetic force between the atoms in your hand and the atoms in the table, a force that emerges from the collective interaction of all those quantum fields. The table is solid because of that emergent force, not in spite of it. In precisely the same way, the emergent picture of gravity does not make it any less potent. It simply reclassifies it. Gravity is not a cosmic puppeteer pulling on invisible strings. It is the universe's most pervasive example of collective behavior, a statistical tendency so powerful it curves the path of light itself. To call it an illusion is not to dismiss it, but to elevate our understanding of it from a simple force to a magnificent and complex consequence of a deeper cosmic order. This apparent perfection, this delicate cosmic balancing act, brings us to a deeply philosophical question. Why does our universe appear so exquisitely fine-tuned for our existence? The strength of gravity is a perfect example. If it were even slightly stronger, the universe would have collapsed back on itself in a fiery crunch moments after the Big Bang. If it were even a tiny bit weaker, matter would have flown apart so rapidly that stars and galaxies could never have coalesced from the primordial gas. We find ourselves in a universe with a gravitational constant that seems perfectly calibrated for the long, slow dance of cosmic structure and the eventual emergence of life. This is the puzzle of the Anthropic Principle. The principle, in its simplest form, suggests that the universe must be compatible with the conscious life that observes it, because we are here to observe it. To some, this feels like a tautology, a cheap excuse that avoids a deeper explanation. It can sound as though we are saying the universe is the way it is because we are here, which seems to put the cart before the horse. But what if this apparent fine-tuning is not a bizarre coincidence or a miraculous act of creation? What if it is an inevitable consequence of the emergent nature of gravity itself? If gravity is not a fundamental force with a freely adjustable constant, but a thermodynamic phenomenon that emerges from a specific quantum system, then its effective strength in our universe is not a random dial setting. It is a fixed outcome. It is determined by the total amount of information in our cosmos and the particular way that information is encoded on the holographic boundary from which our reality is projected. We do not live in a universe with a special, finely tuned gravitational constant. We live in the only kind of universe that can emerge from this specific underlying quantum state, a state that necessarily produces the gravitational pull we measure. Our existence is not a lucky accident within a cosmos of infinite possibilities. It is woven directly into the fabric of the cosmic explanation. We are not observers of a pre-built stage. We are participants in a reality whose very laws, including the force of gravity, are a direct reflection of the quantum information that constitutes us. The question shifts from why is the universe so perfect for life to why is the quantum code of our universe written in this specific way. This transforms a potential miracle into a profound and perhaps ultimately answerable scientific mystery. The ultimate technological payoff of this new understanding may lie not in controlling gravity, but in harnessing the very fabric of reality for computation. If spacetime is a network of entangled quantum information, then manipulating that network could unlock computational powers we can barely conceive. We are already building the first primitive quantum computers that exploit entanglement to solve problems intractable for classical machines. But these devices operate within the spacetime stage. A future quantum computer that understands its own stage as an emergent property could manipulate the underlying spin network directly. It would not just compute with qubits, it would compute with the geometry of space itself, performing calculations by subtly tweaking the entanglement patterns that define distance and time. This is not about creating gravity motors, but about building a universe-scale processor. Such a machine could simulate complex systems, from the birth of a galaxy to the folding of a protein, with a fidelity that is indistinguishable from reality, because it would be operating on the same fundamental level. The energy implications are equally staggering. The quantum vacuum is not empty, it is a seething reservoir of zero-point energy. Tapping this energy has long been a dream of physics, but it seemed forever out of reach because the energy is locked in a perfectly balanced neutral state. However, if spacetime is emergent, that balance is a consequence of the holographic encoding. In principle, a deep enough understanding could allow us to create a local imbalance, a tiny crack in the fabric from which useful energy could be extracted. This is analogous to the Penrose process, a theoretical method where energy is drawn from the spinning spacetime around a rotating black hole. In our emergent reality, we would not need a black hole. We would only need to learn the language of the cosmic code to create similar, controlled effects on a microscopic scale. This would not violate any laws of thermodynamics. It would simply be a matter of accessing a deeper layer of the energy landscape. The most transformative applications, however, are likely those we cannot yet imagine. When James Clerk Maxwell unified electricity and magnetism into a single theory of electromagnetism in the 19th century, he could not have foreseen the global internet, smartphones, or magnetic resonance imaging. He was describing the fundamental behavior of light. The technological revolution that followed was an unforeseen consequence of understanding a deeper layer of reality. Our quest to understand emergent gravity is the same. We are peering into the source code of the cosmos, and while we might dream of anti-gravity, the real revolution will probably be something entirely unexpected, a technology that rewrites our concept of the possible, born from finally reading the universe's own blueprint. This speculative thread leads us to the most profound and controversial frontier, the possible role of consciousness itself. We must tread carefully here, for we are leaving the solid ground of established science and entering a realm of pure, fascinating speculation where no consensus exists. Yet it is a question so compelling it demands to be asked. The renowned physicist Roger Penrose, together with anesthesiologist Stuart Hameroff, proposed a theory called orchestrated objective reduction. They suggested that the mysterious collapse of the quantum wave function, the moment a particle's possibilities solidify into a single reality, is not a random event but a gravitational one. In their view, tiny structures within the brain's neurons can maintain quantum coherence, and when these quantum states become too massive, their own minute gravitational fields cause them to collapse, and this orchestrated collapse is the very basis of conscious experience. Now, place this radical idea within the framework of emergent gravity. If gravity itself is not fundamental but emerges from a quantum informational substrate, then the proposed link between gravity and consciousness becomes even more abstract and profound. It suggests that both our minds and the force that shapes the cosmos might be drawing from the same deep well. The question then transforms. If the reality we perceive, the very fabric of space and time and force, is a magnificent illusion emerging from a network of quantum information, then what is our own conscious awareness? Could it be that our inner experience, the feeling of being, is not some ghost in the machine but an emergent phenomenon of a similar kind? Perhaps the brain is not just a computer made of meat, but a dense, complex network that has learned to tap into the fundamental informational processes of the universe, giving rise to a self-aware pattern from the cosmic computation. This is not a statement of fact, but the ultimate open question that this entire journey points toward. It hints that the force that binds the stars and the light by which we see them might both be stories told by the same underlying mysterious reality. The classroom of the future might look very different from the one you remember. If the emergent view of gravity were confirmed, it would revolutionize not just our theories, but how we pass on the story of the cosmos to the next generation. The entire physics curriculum would be rewritten from the ground up. We would no longer present Isaac Newton's laws and Einstein's general relativity as the ultimate fundamental description of gravity. Instead, they would be taught for what they truly are: incredibly powerful and accurate effective field theories. They are the perfect tools for sending a satellite to Mars or predicting the orbit of Mercury, magnificent approximations that work flawlessly within their domain, much like Newton's laws are a perfect approximation of relativity for everyday speeds. But they would no longer be the end of the story. They would be the gateway. From the very first introductory courses, students would be introduced to the holographic principle. They would learn that space and time are not a given, but a collective consequence. The force that pulls an apple from a tree would be presented not as a mysterious attraction, but as an entropic tendency, a statistical drive born from the quantum information woven into the fabric of reality. This shift in narrative is profound. It moves the story of physical law away from a tale of fundamental forces acting at a distance, and toward a story of information, connection, and emergence. It fosters a more holistic and modern understanding, where the universe is seen not as a collection of separate things, but as a vast, interconnected network. A student learning about a planet's orbit would understand it not as being pulled by a force, but as following a path of maximum entropy through a geometry built from quantum entanglement. This is not just a new fact to memorize, it is a new way of seeing. It bridges the chasm between the tiny quantum world and the vast cosmos, showing they are part of a single, coherent story. Such an education would equip young minds not with a static set of answers, but with a dynamic and evolving picture of reality, preparing them for the next great discoveries that will surely continue to reshape our place in the universe. We began with the solid certainty of a falling apple and end with the ethereal possibility that the force which brought it down is a cosmic phantasm, Our journey has taken us from Newton's mysterious action at a distance to Einstein's geometric warping of spacetime, and finally into the heart of a quantum revolution. We witnessed the epic clash between the smooth, deterministic cosmos of general relativity and the chaotic, probabilistic world of quantum mechanics, a schism that screams for a deeper resolution. That resolution appears to be the radical principle of emergence. We explored the holographic idea that our three-dimensional reality is a projection from a two-dimensional boundary, a cosmic illusion of staggering complexity. We saw how gravity could be an entropic force, a thermodynamic tendency for the universe to maximize its disorder, much like the pull of a stretched rubber band. And at the very core of it all, we found the ghostly glue of quantum entanglement, the fundamental weaver that stitches together the very fabric of space and time from a formless dust of information. This vision is not yet complete. It faces formidable challenges and competing ideas, but it stands as one of the most profound and promising pathways in our quest for a final theory. To accept that gravity is an emergent illusion is not to diminish the wonder of the universe. It is to reveal a far grander and more elegant reality, a cosmos where everything is deeply and fundamentally interconnected. The force that grounds you is a story written in the language of quantum information. So tell me, which thread of this emergent reality captures your imagination the most? Is it the holographic universe, the entropic force, or the idea that spacetime itself is woven from entanglement? Let the conversation continue in the comments.